All right. Well, thank you all for being here. Thank you for having us. Thank you to Jigwell for spending a lot of time on our paper. So this is a joint work with Willie, who's here, and Satoshi, who's in California. And the title is a Trilemma for Asset Demand Estimation. Okay, so the motivation for this paper is kind of straightforward. So as you all know, there's influential literature in asset pricing that tries to use sort of various forms of portfolio data in order to estimate, how people pick their portfolios, how important investors pick their portfolios, with the goal sort of understanding sort of important questions: how are asset prices determined, how are shocks accommodated, how is policy transmitted, and so forth. Now, by and large, I think it's fair to say that sort of either explicitly or implicitly, the paradigm that sort of underlies most of the methods or approaches in this literature follow the sort of classic Marshallian paradigm of demand estimation, by which I mean that, you can imagine a world in which sort of people's choices are jointly determined by a bunch of different forces. And the Marshallian paradigm to some extent says, yeah, maybe we can usefully summarize all of those forces using sort of a stable demand function for a given asset as a function of its price. And sort of accordingly, if you read the literature, a lot of the findings are sort of reported in language closely associated with this, like what is the elasticity of demand for a certain asset, what's the inverse of that, the price multiplier, and so forth. Now, one tricky thing with this is that obviously in order to estimate the slope of a demand curve, you need sort of clean variation that allows you to trace out that function. And so in asset pricing, that typically means you need sort of variation in a single price holding all the other prices, all the other relevant asset prices fixed. Okay, and now empirically, obviously, you don't generally see exogenous price variation, and so the way the Marshallian paradigm sort of operates is to say, okay, we're going to try to create as if random price variation using supply shocks. Okay, and then use those supply shocks and the response to that to trace out the supply curve. And again, sort of the promise of this is that once you have, if that works well, and you've identified sort of a stable demand curve, you can use this to try to run counterfactuals, understand policy, and so forth. And so our paper is basically trying to take a relatively big picture approach and ask, is this sort of Marshallian paradigm the right way to estimate and structure portfolio data? Okay? And the sort of more precise version of that question is that we want to establish under what conditions you can identify sort of asset level demand elasticities or demand slopes from observational data with supply shocks without sort of strong a priori theoretical restrictions on what those demand functions look like. Our basic result is sort of going to be structured in a trilemma, which is that we're going to argue that you cannot jointly maintain sort of two canonical principles of asset pricing and then sort of the basic Marshallian view, by which we mean, the first leg is investors have preferences over payoffs, so they care about the cash flows generated by the assets as opposed to the assets directly. Second, prices satisfy no arbitrage. And then the third, and this is the Marshallian piece, is that asset demand functions are invariant, that is, do not shift in response to even perfectly exogenous demand curves. Okay, so that one means that basically, even if you get a perfectly clean supply shock, the underlying demand function need not be stable. Okay, the only exception to this we'll document is that if you had an asset menu that was purely consisted purely of arrow securities, where there's sort of no overlap in the cash flow distribution. Okay, and so the takeaway from this, in our view at least, is not that sort of estimates in the literature are uninformative, but rather that you should think of reported elasticities or demand slopes as at least to a large extent also reflecting sort of a priori theoretical structure as opposed to just the data. Okay, so before I get into all the details, let me walk you through sort of a simple example that I think highlights all of these, the interplay of all of these different pieces. Okay, so I want to, imagine an investor who's choosing a portfolio, in a simple 2x2 world. Okay, there's two assets, those are the rows, and then there's two states of the world, those are the columns. Okay, and preferences for payoffs. Again, what we mean by that is that investor, at least in part, cares about the cash flows produced by this asset as opposed to just owning asset 1 versus asset 2, right? And so a consequence of this is, in general, demand functions for these individual assets, so the quantities chosen of these individual assets are going to depend sort of non-separably on both of these assets, right? Because they're substitutes to some extent. Okay, now, no arbitrage, obviously, we all know, says in this world, asset prices P1 and P2 are going to be linear in the underlying state prices. And so, for example, price of asset 1 is 1 times the state 1 state price, and then A times Q2, and so on for. Now, once you have that structure in place, you can imagine what it means to try to estimate a demand elasticity. What's the price variation that you want? You want P1, let's say, to move while holding P2 fixed, right? That would get you isolate a single price movement. Okay, now if you stare at these equations, it's kind of, this means something specific about what has to happen implicitly to the underlying state prices. And so in this particular case, Q1 would have to go up, and Q2 would have to decrease. Okay, that's the way you could get P1 to move while holding P2 fixed. Now, think about what a supply shock does. Okay, so if you think about shocking, let's say, the supply of asset 1, that asset pays off in both states of the world, right? So it increases or decreases the amount of consumption that's available to this investor in that state of the world, all else equal. Now, if this investor has sort of standard downward sloping demand curves for state contingent consumption, the state prices in response to this supply shock have to move in lockstep. They either go up together or down together. And so what that's going to mean is that the supply shocks generically are going to generate sort of misaligned state price movements as opposed to what the ideal experiment requires. Okay, and so we're going to argue that that's sort of a generic problem. It's a prevalent problem, and for realistic sort of payoff processes, you're always generically going to get this misalignment, unless, of course, you set A and B to 0, and you have arrow securities, and there's no cross-asset linkages. So that's the basic paper. Okay, and again, if you're wondering sort of in the back of your head, what's different here from standard I/O goods markets, we think there's sort of 3 important characteristics. One is that investors do not sort of have direct preferences over the goods. They have instrumental preference for assets because they care about the cash flows. Second is that, a car you cannot unbundle. A financial asset you can through portfolio formation. That requires some restrictions on cross prices, namely no arbitrage. And then as a result of that, the geometry of those, cross price restrictions from no arbitrage, they're basically going to prevent supply shocks from generating the right variation. Okay, so that's the paper in a nutshell. So if you like sort of thinking through this in the Marshallian view, right, the takeaway picture for us at least is, the ideal scenario is you have a demand function that depends on sort of an individual asset price and the vector of other asset prices. That thing is stable. You shock the supply exogenously. You move along it, and in our case, what happens is, our argument is that at least in arbitrage-free financial markets, where you have this geometry of cross-price restrictions, whenever you shock the supply curve, there's a simultaneous shift in the underlying demand curve, and so you cannot move along basically a fixed demand curve. Okay, so let me walk you through the details. So the framework we're going to use is very, very standard. We're going to study a static model, like a 2-date model. That's supposed to eliminate sort of additional challenges that come from dynamic trading. Jigo has a paper on that. Christian Upp and Jules have a paper on that. So we're going to ignore those. Issues here. Now there's going to be standard form of uncertainty. One of Z states is going to be realized at date 1. Investors are going to choose among J assets. So the asset menu is a primitive of the problem. Okay, we're going to summarize the payoffs using a Y as the J by Z payoff matrix. And just to give sort of a clear benchmark, we're going to study sort of weakly positive assets with weakly positive payoffs. We're going to allow markets to be complete or incomplete. That's not going to make a big difference. For notation, P is the vector of asset prices. Q is the vector of state prices, which we all understand need not be unique. And then much like the literature, we're sort of going to try to understand investor level demand functions. And so we're going to imagine sort of potentially heterogeneous investors indexed by I. It's an endowment economy. They're born with some endowment of assets, and then the aggregate endowment is, the sum of that. And then if we need to close the model, we're just going to study competitive equilibrium where prices clear markets. So completely standard framework. Okay, so part one, first leg of the trilemma is preferences over payoffs. Okay, so we're going to study a completely standard decision problem, maximizing utility over two states of the world, subject to the budget constraint, and potential constraints on portfolio formation. Okay, so you may have some restrictions on which assets you can buy or not. And then C0, just for consistency, we're going to treat that as the numeraire good. So everything, all the prices are with respect to relative prices with respect to the time zero consumption. You can easily enrich this problem with sort of some form of preferences over assets due to ESG or something. The important thing is that even if that's true, you do care about preferences over payoffs directly. And you can, of course, add things like non-traded endowments and so on. None of that really makes a difference. Okay, so in terms of what the Marshallian paradigm sort of implies is, one view of the world is, oh, there's a bunch of fundamental parameters here, and you might care about identifying all of those individually. Or you can say, well, I don't need to know all of them individually. I'm going to try to characterize the outcome of the decision problem using sort of asset level demand functions. And that's I think a fair description of most of the literature, and so we're going to follow that. And the key upshot here is, to the extent that assets have overlapping payoffs, so they might pay off in different states, in similar states of the world, that Marshallian demand function in the canonical sort of portfolio choice problem is going to depend on all of these asset prices jointly. Okay, so it's non-separable. Okay, and that's obviously a key feature. Okay, part two. No arbitrage. So, you may not need to be convinced of this. You may say, I definitely want to maintain no arbitrage. Even if you didn't, there's a couple of reasons why no arbitrage is important even for demand analysis, right? So obviously, one important benefit of it is it ensures sort of a well-behaved the existence of a well-behaved portfolio choice solution. So that's important. The second is, if you look at a lot of practical applications of this kind of method, you typically have a large set of assets, right? So you may have thousands of assets or 500 assets to invest in and so forth. And so you have a sort of a curse of dimensionality going on. And the way to reduce the dimensionality is what a lot of people do is study demand for factor portfolios or other sort of more aggregated portfolios. That obviously is convenient. For that, it's obviously convenient to have no arbitrage to have consistent pricing. And then finally, part of this literature is interested in counterfactuals. I think for that, again, no arbitrage is sort of an important consistency requirement on the price system. Okay, so we're just going to assert this in the strict form. There is no arbitrage. Prices satisfy payoff matrix times the vector of state prices, and hopefully it'll become clear that, at least we think, if you mess around with this a little bit and there's sort of a little bit of arbitrage, some small deviations from this, it's not going to invalidate the main point. Okay, so now comes the important part. Why does that combination mean that demand curves are generally going to be unstable? Okay, so what is the idea of sort of a Marshallian demand curve? It's supposed to answer a hypothetical, right? It's supposed to address a hypothetical thought experiment, which is, how does demand change if I were to vary the price of a given asset but kept everything else fixed? And so the simple observation in our paper, and that we're going to build everything else on, is that you can sort of conceptualize that thought experiment quite nicely using the language of state prices, okay? So in particular, you could equally say, how does the investor respond to the state price changes induced by a shock to a given asset price, right? That would be sort of an equivalent statement, at least under no arbitrage, of that thought experiment. Now, the nice thing is you have a clear answer on what those induced state price changes are going to be. So we're going to use, because we want to accommodate incomplete markets, we're going to use the generalized Moore-Penrose inverse. And under no arbitrage, you can write state prices as a function of asset prices, just like this. Y inverse times the vector of asset prices. Now, the ideal thought experiment, again, is that you vary a single asset price, holding everything else fixed. And so that has a very clear representation in state price language. It's this, okay? The ideal price variation in terms of state prices that you want to identify the demand curve is just given by this small price shock. What is it proportional to? It's the inverse payoff matrix. Okay, so it's uniquely, up to picking an inverse, it's uniquely pinned down by this. Okay, and the thing I want you to keep in mind here is that this ideal state price variation is proportional to the inverse, again, to the inverse payoff matrix. Okay, so that's the important piece. Now, what do supply shocks do? So again, we're going to, we don't want to take any stand on whether a particular instrument is good, whether a particular supply shock is clean or not. We're going to imagine a theoretical laboratory where you have a perfectly exogenous shock to the supply of a given asset. So just imagine sort of an outside investor helicopter dropping assets onto for purely exogenous reasons. Okay, and then our question is, does that induced price variation align with what is required to estimate a stable asset level demand curve? Now, we're going to, try to, you have to take a little bit of a stand on what, the structure of the economy is here, okay? Otherwise, you cannot reason through what a supply shock will do. So we're going to try to be minimal. And so, again, we're going to imagine a shock to the aggregate asset endowment. And we're going to consider economies with downward sloping consumption demand, okay? By which, formally, we mean that there exists some matrix, Z by Z, so Z is the number of states, Z by Z matrix V, with strictly positive diagonal elements such that the supply shock generates state price changes that look like this, that are proportional to the payoffs. Okay, so the idea here, what is V supposed to capture is the marginal pricing kernel, the slope of the pricing kernel. And it says that if I get more state contingent consumption, then the state price in that state has to fall. Okay, so it's non-satiation, basically downward sloping demand for state contingent consumption. Okay, so this is sort of another advantage of casting everything in state prices, because you can make a statement on supply shocks without sort of specifying, taking too strong of a stand on the asset menu or something. This is a statement on margin utility of consumption. Now, and again, the diagonal elements here, why do we put a structure on the diagonal elements? Those are sort of the direct effects of what you buy. There's more of this asset. This pays off in state one. State price one falls. Okay, so that's what the diagonal elements capture. And you can already see where we're going, right? Now the problem here is going to be that the state price changes induced by supply shocks, I think very reasonably, are going to be proportional to the payoff matrix itself, not its inverse. Okay, and so that's going to create the problem of misalignment. Okay, now one thing I haven't told you so far is what about the off-diagonal elements of V? And the way you want to think about the off-diagonals here is that they capture potential direct spillovers in state prices. Okay, so I shock the supply of consumption in state one, but not in state two. But I may have a model in which, for example, because of non-separable preferences, that directly affects the state price in state two as well. Okay, now hopefully it's relatively intuitive that generically those types of additional linkages are going to make identification of demand curves harder, because they sort of create direct spillovers across state prices, and those are really what you want to avoid potentially. Okay, and so what we're going to assume, sort of to give stable demand curves the best shot, is that the off-diagonal elements are all zero. Okay, so that this V, this marginal pricing kernel, is a diagonal matrix. Okay, okay. So now, with that in mind, we can sort of define formal conditions on what it means for a supply shock to give the right state price variation. The first one is sort of the strictest, and in principle, what you want is you would say, okay, Q ideal, or delta Q ideal, that's the state price variation I want. This is what the supply shock generates. I'm going to allow the econometrician to sort of scale up and down the supply shock by some scalar. That seems fine. But other than that, I want these things to align exactly. Okay, and so that's in principle what you want to identify demand curves. You can have a slightly weaker. You can have a slightly weaker criterion, slightly less ambitious. You might say, I want at least the direction of these state price changes to be the same. Okay, if the ideal supply, the ideal experiment calls for state 1 consumption to become cheaper, I want the supply shock to replicate that directionally. Okay, if that's violated, that's obviously a problem for estimating substitution patterns, because stuff that's supposed to become cheaper may actually become more expensive. Okay, so that's the second sort of weaker consistency requirement. So then here's sort of our main result. We're going to define assets as having overlapping payoffs. Okay, here J and J prime, if you can find at least one state of the world such that both of these assets have strictly positive payoffs. Okay, and then our result is, if you want either the weak or the strict condition to be satisfied, then it must be the case that there are no assets with overlapping payoffs. And in the special case that markets are complete, that means Y is diagonal up to permutations. Okay, so we have arrow, so we must have arrow securities. Okay, now this turns out to be a simple linear algebra thing from 1972, but you can obviously see the intuition for what's going on here. The problem is, one thing is proportional to Y, the other one is proportional to Y inverse. They don't generally align unless you have diagonal matrices. And then why do we get these sign switches? Well, remember what we're trying to do, right? We're trying to figure out the price of arrow securities. And so if you have assets that pay off in multiple states, you have to zero out the payoffs in some states of the world, and that's going to get you negative signs in the inverse. And so you're going to generally get misalignment. Okay. So again, just at a high level, what's going on here, right? The mental model is asset supply shocks affect behavior because they change the price, they change the cost of payoffs. Under no arbitrage, you have a particular form of cross-price restrictions that has to be satisfied, and those geometrically are sort of the wrong direction as what you would want to get from the ideal experiment. The only way to get around this is arrow securities. Okay? Now, I want to point out one thing, which is sort of obvious, but I think sometimes slips through the cracks a little bit, is that this is a condition that says no overlapping payoffs. Okay, there shouldn't be states of the world in which both assets pay off. That's obviously a much stronger condition than requiring assets to be orthogonal or something like that. Okay, and so simply orthogonalizing assets into factor portfolios, for example, isn't going to do the job. Now, another sort of useful intuition is what's going on here relative to standard I/O? Well, if you're in an arrow security world, then you do have direct preferences over assets because they measure what you care about, and so you sort of collapse this instrumental demand problem. Okay, now, so far, what I showed you is that there are issues, and so you may reasonably ask, well, how severe are these issues? Is this like, happen all over the payoff matrix once in a while? What's going on? And so we try to do some characterization on the prevalence of these issues. Okay. So first, sort of just as a theoretical guarantee, so far, I wanted alignment on the entire matrix, and so you may have wondered, is it true that every asset the experiment for every asset is going to be misaligned? Is there a wrong sign sort of in every row of the inverse payoff matrix? And that's sort of easy as long as you have a condition on the columns of the payoff matrix. So for each state there's at least two assets that pay off, then every asset is going to have at least one wrong sign. The second, and I think sort of more important thing we do is, one problem is that all of our conditions here are stated on the payoff matrix, which in principle is unobservable and at least latent to the econometrician, right? And so you may wonder, sort of, for realistic payoff processes, what's the extent of this misalignment? And so what we're going to do basically is use random matrix theory, and we're going to study basically random matrices drawn from sort of an underlying payoff distribution, which sort of has a realistic factor structure. Okay, I'll show you results for a single factor structure, but it could be multiple factors. And then, because this stuff is random, we're going to study asymptotics to begin with. Okay, and so first we're going to take the limit as the number of states become very large, and then you're going to characterize what happens as the number of assets also increases. Okay, so in the limit, you have this kind of striking result that at least half of the state price changes are going to have, a negative sign or the flipped sign compared to what they should be. So in our benchmark where the payoff matrix is positive, that means all of these signs should be positive, but half of the signs are negative. And then, perhaps a little bit more strikingly, once you think about it, you could have imagined, oh, maybe once I figure out where the wrong signs are, I can devise some procedure to deal with it, to control for this. And here you have the problem that it turns out that the sign of every single element is a coin flip. Okay, so there's no stability in this process at all. Okay, and so loosely speaking, the intuition you may have is, I have these assets, they have sort of similar payoffs in certain states of the world, and now I have to pick which one to zero out. So which element to zero out? How do I construct the error security matrix? And then it matters a lot which one's slightly higher than slightly lower, and that gives you a lot of instability here. Okay, if you do sort of a Mickey Mouse empirical exercise where you draw payoffs from the S&P 500 at random, you get sort of very similar results that you get sort of 50% of these elements having the wrong sign. So here's just an illustration of this, that this is not sort of a kooky asymptotic result. This is the fraction of positive signs as a function of the number of assets. This is the asymptotic limit 0.5. This is our characterization of sort of the rate of convergence. So this is a constant, and then this is the number of assets. And you can see that even if you have 20 assets or something like that, you're going to get very close to 50% assets having the wrong sign. Okay, so I think from our perspective, this sort of illustrates that there's a big problem of instability and misalignment between ideal and supply shocks. Now, you may wonder, what does this mean for demand elasticities at the asset level? Okay, so once I have these problems at the state price level and I aggregate them up to asset demand, how much bias is there? Okay, and so here's a very simple way to sort of illustrate the mechanics of this and walk through the intuition. So we're going to study a model with a representative investor with log utility, aggregate endowment fixed to 1. This should remind you of my example at the beginning. So we have a simple 2x2 world. There's a green asset and a green state, a red asset and a red state. The green asset pays off a little more in the green state, and the red asset pays off a little bit more in the red state. And we have a simple parameter here, epsilon, which measures the degree of substitution between these assets. If epsilon is 1, then we're in error security world. If epsilon is 0, then they're perfect substitutes. Okay? And now, again, you can sort of walk through the math here quite simply. No arbitrage tells you state prices have to look like this. Okay, that's just and then if you changed the price of the green asset only, what would need to happen is that the state price of the green state would have to go up and the red state price would have to fall in equilibrium, because both of these assets pay off in both states. That's not going to be the case. Both state prices are going to move in lockstep. Okay, so this is as a function of the complementarity, the observed change in asset holdings as a function, or the observed demand slope as a function of what happens in the supply shock and in the theoretical hypothetical idea where you just vary a single asset price. And what you see is the supply shock, because it affects sort of both assets relatively symmetrically, because these state prices have to move in lockstep. There's going to be very little responsiveness, whereas in the hypothetical where you could have moved just one price, you get a massive difference, and these are sort of orders of magnitude different. Okay, I have like a minute, so let me say sort of a couple of things you might do to overcome and address the trilemma. Okay, so very loosely, you could just impose a priori restrictions on the payoff matrix. On the decision problem. And so here, for example, it's a linearization, okay, where you just say, I'm going to assume I can well approximate the overall demand system using a simple linear substitution matrix. Then our result is that even in that case, you need many experiments. So if you want to properly identify this thing under non-separable demand, you need as many independent experiments, as many clean individual shocks as number of acids. Otherwise, you just see a projection. Again, sort of highlighting this point that you can get numbers, but those numbers are going to be influenced by the a priori restrictions that you put on them. Jigwell and Koinyogo's, I think, work is examples of the structural approach where you say I'm going to just make certain assumptions on the substitution matrix, and again under those assumptions you can identify that structure. But our previous work on this, which dealt mainly with the Koinyogo paper, again says you have to be cautious that if you misspecify those cross-acid interactions that are sort of endemic, you're going to potentially create large biases. The last thing I'll say is that you may be able to find settings in which you have richer data, non-observational data, or sort of shocks to taxes or transaction costs that shift de facto prices without needing to move equilibrium prices. So I'll end there. So we're going to argue that, in sum, that three central properties of acid pricing and demand estimation cannot jointly hold.
Let's turn to the discussion.
I'm sorry.
This is going to come out of the question time.
I'm sorry.
That's okay.
Yep.